Morphology of bacteria. Microorganisms are a heterogeneous group of several distinct classes of living beings. They come under the kingdom Protista. Based on the differences in cellular organization and biochemistry, they are classified into prokaryotes and eukaryotes. Under prokaryotes, you can see bacteria and blue-green algae. Eukaryotes comprise fungi, other algae, slime molds, protozoa. Bacteria are prokaryotic microorganisms that do not contain chlorophyll. Unicellular, do not show true branching except in higher bacteria, that is actinomycetales. Size of bacteria. The unit of measurement used in bacteriology is micron, micrometer. 1 micron or 1 micrometer is equal to 1 by 1000th of a millimeter. 1 millimicron or nanometer, 1 nanometer is equal to 1 by 1000, that is 1000th of a micron or 1 millionth of a millimeter. 1 angstrom unit is equal to 1/10 of a nanometer. The limit of resolution with the unaided eye is about 200 microns. Bacteria, being much smaller, can be visualized only under magnification. Bacteria of medical importance generally measure 0.2 to 1.5 micrometer in diameter, 3 to 5 micrometer in length. Prokaryote. In prokaryote, you can see cell wall, cell membrane, which is the site of cellular respiration. A single circular chromosome is seen, and cytoplasm rich in ribosomes. And the chemical composition, you can see muramic acid. This is eukaryote. In which we can find nucleus, nuclear membrane, nucleolus, deoxyribonucleoprotein, and chromosome more than one are seen. And cytoplasm, you can see cytoplasmic streaming, pinocytosis, mitochondria, lysosomes, Golgi apparatus, endoplasmic reticulum. And the chemical composition for an eukaryote, sterols are present. So the main difference between a prokaryote and eukaryote is in prokaryote we can't find any nucleus. Microscopy. Leeuwenhoek first observed bacteria over 300 years ago using hand ground lenses. Optical or light microscope. Bacteria may be examined under the compound microscope either in living state or after fixation and staining. Examination of wet films or hanging drops indicate shape, arrangement, motility, approximate size of the cells. But due to lack of contrast, details cannot be appreciated. This is the principle of bright field or light microscopy. Specimen which is magnified, this is the magnified image. Light microscope, in which you can see ocular lens, objective lens, condenser lens, and this is the specimen on the slide. light source. Phase contrast microscopy. This improves contrast, makes evident structures within cells that differ in thickness or refractive index. Differences in refractive index between bacterial cells and surrounding medium make them clearly visible. In phase contrast microscopy, phase differences are converted into differences in intensity of light, producing light and dark contrast in the image. Fluorescent microscope. This uses light of a high intensity source which excites a fluorescent agent, which in turn emits a low energy light of a longer wavelength that produces the image. Here you can see this is the light source, high intensity light source, which excites a fluorescent agent, which in turn emits a low energy light of a longer wavelength that produces the image. The fluorescent light can be separated from the surrounding radiation using filters designed for that specific wavelength, allowing the viewer to see only that which shows fluorescence. Microorganisms in a specimen can be stained with a fluorescent dye. On exposure to excitation light, organisms are visually detected by the emission of a fluorescent light by the dye which they have been stained. So, the staining can be of two types, fluorochroming and immunofluorescence. Fluorochroming involves non-specific staining of any bacterial cell with a fluorescent dye. Immunofluorescence uses antibodies labeled with fluorescent dye, a conjugate, to specifically stain a bacterial species. As here you can see, in fluorochroming, a fluorescent dye for which the target bacteria to be stained, and all bacteria flourish. And immunofluorescence, in this type of staining, the fluorescent dye specific antibody, this is the conjugate. Here the specific bacteria which is having the specific antigen. Now this fluorescent dye is seen only for the specifically it stains only particular bacterial species. Dark field or dark ground microscope. Another method of improving the contrast is the dark field or dark ground microscope, in which reflected light is used instead of transmitted light used in the ordinary microscope. The essential part of the dark field microscope is the dark field condenser. As in here you can see dark field microscope. Here reflected light is used. Reflected light is used instead of transmitted light. Generally in an ordinary microscope, normal transmitted light is used. The essential part of the dark field microscope is the dark field condenser with a central circular stop which illuminates the object with a cone of light without letting any ray of light fall directly on the objective lens. Light rays falling on the object are reflected or scattered onto the objective lens, with the result that object appears self-luminous against a dark background. The contrast gives an illusion of increased resolution so that very slender organisms such as spirochetes. This is a bit because spirochetes can be seen in dark ground microscope or dark field microscope. The resolving power of light microscope is limited by wavelength of light. In order to be seen and delineated, an object has to have a size of approximately half the wavelength of the light used. With visible light using the best optical systems, limit of resolution is about 300 nanometers. Two specialized types of microscopes. Interference microscope reveals cell organelles, enables quantitative measurement of chemical constituents of cells, such as lipids, proteins, and nucleic acids. Polarization microscope enables study of intracellular structures using differences in birefringence. Electron microscope. Here, a beam of electrons is used instead of the beam of light used in optical microscope. The electron beam is focused by circular electromagnets, which are analogous to lenses in the light microscope. The object which is held in the path of the beam scatters the electrons and produces an image which is focused on a fluorescent viewing screen. As wavelength of electrons used is approximately 0.005 nanometer, wherein 500 nanometers with visible light. Resolving power is 0.1 nanometer for the electron microscope. Shadow casting technique with vaporized heavy metals. Pictures with good contrast and 3D effect is possible. Negative staining technique with phosphotungstic acid, another valuable technique in studying fine structure. Gas molecules scatter electrons and therefore necessary to examine the object in a vacuum. Hence, only dead and dried objects can be examined in the electron microscope. This may lead to considerable distortion in cell morphology. Freeze etching, deep freezing of specimens in a liquid gas and subsequent formation of carbon platinum replicas of the material. Since such frozen cells may remain viable, freeze etching enables the study of cellular ultrastructure as it appears in the living state.